Kachi, and this is the online class. We'll be taking description and purposes of fields. A field can be defined as a region of space under the influence of gravitation, magnetism, and electricity. That means looking at these diagrams, electric field, magnetic field, gravitational field, we can see these lines where if a body is in these lines, this one, that means it's under the field of the thing. We have forces. There are two types of forces as we discussed in our previous classes. We have the contact force and the force field. So taking the force field. What are force field? They are forces which source does not require contact with the body to which they are applied. So examples of them include gravitational force, electric force, and magnetic force. So these force fields, there are also two types, which are the scalar and vector. From our previous knowledge in our previous class, scalar fields are those that have magnitude but no direction. So we have examples as energy, temperature, and source of that. Vector fields, they have both magnitude and direction, which are we have examples as gravitational fields, magnetic and electric fields. So moving to gravitational field. Gravitational field is a region of space around a mass in which gravitational force of the mass can be felt. That means like this diagram you see. So this place, the arrows pointing that is the field. So another definition is a force field and influences the motion of objects in the space where it operates without coming in contact with the object. So gravitational fields. An example is when an object is thrown upwards. So if it's thrown upwards, just like our normal real life example, it's observed that when they move upward, they stay momentarily at rest and eventually move downwards. That means, like if we throw a stone now, we also observe it that they go up and seem as if they stay up for a little while, then they come down. So these are the influence of gravitational force acting on them. So gravitational fields, we have observed that it shows that objects move upward against gravity and not fully objects do so with an acceleration due to gravity. That means gravity is acting downwards. So if you move upwards, that means you are going against gravity. The other one, not falling objects do so with an acceleration due to gravity. That means this force has a phenomenon behind it, which we call acceleration due to gravity. So acceleration due to gravity. Acceleration due to gravity is called is denoted as g, and we have its every value as 9.81 meter per second squared. So for this acceleration due to gravity, it is uniform at a place for all bodies irrespective of their mass, but vary from one place to another. It's not like weight. It is minimum at the equator and maximum at the poles. That means it varies from place to place. And why it's such is that the earth has different radius in different parts of the earth. So, and again, what we can learn about acceleration due to gravity in free fall or absence of resistance. If two masses are released from the same point, they fall to the ground simultaneously. Like when we have a stone and a feather. If there is absence of air resistance, both will fall will reach the ground at the same time. Because we are used to the fact that a stone will fall before a feather. That is wrong if there is absence of air resistance. So moving to magnetism, the second one we talk about. Magnetic field is a region of space where the force of a magnet is felt. It causes magnetic objects to be attracted or repelled from it when the object is placed in its field. Like we've observed the when we bring a magnetic material near a magnet, we observe that when it's close very near to it, they attract something like that. So like we have an example here, is when we bring a magnet close to iron filings. It's observed that the iron filings attract the magnet when placed close to it. So it's a normal example we do try. Even we bring the magnet close to the iron filings, there will be forces of attraction. That means that we place in the magnet's field. So this is an illustration. That means when I bring a magnet, when I bring this is a magnet, when I bring a magnetic substance like the iron filings, in this place where this arrow when this arrow is to attract. But when it's somewhere like here where the arrow cannot touch, cannot attract. So magnet and magnetic substance. A bar magnet suspended about the center in such a way to swing freely quickly comes to rest in geographic north-south direction. So that's how we can differentiate a magnet from any other magnetic material or sorts of that. They come to rest in geographical north-south direction. And a magnet can attract pieces of iron and such because those iron and nickel they are called the magnetic substance because they are attracted by the iron, by the magnet. And the ability of the magnet to attract magnetic substance is called magnetism. So from this illustration, we can see that this magnet, this is the north pole, this is south pole, it comes to rest in our geographical north and geographical south. That's how we differentiate magnet from other materials. So magnetism and magnetic substance. We observe that when iron filings are attracted by a magnet, it's concentrated at the ends of the magnet, which are called the poles. But I've tried it before. When we have a magnet, we tend to see the iron filings or the needles or what or sorts. They attach very well to the ends of the magnet. So, and they are called the poles. Therefore, we can now say the poles of the magnet is the region where the power or strength of the magnet is concentrated. That means where there is more of attraction. So, as you can see, this is an end of the magnet. This is a pole. This is a pole. This is a pole. This is a pole. This is a bar magnet. This is an Austrian magnet. All these illustrations are poles. So the diagram shows the pole of magnets where the magnetic attraction seems strongest. As I've explained. Poles and observations. There are two poles of a magnet. So these are we have the north pole and the south pole. So for the north pole, it's the end of the magnet that points to the northward direction, while south pole is the end of the magnet that points southward direction. So that's how we differentiate north pole from south pole. So poles and observations. From observation and experiment, if we bring the north pole of another magnet to the north pole of the suspended magnet, there is a force of repulsion. Likewise, if we bring the south pole of another magnet to the south pole of one magnet, there is also repulsion. And if reverse is tried, the north pole is broader than the south pole. There's a force of attraction and vice versa. We might have tried it before, like the north pole. Might have tried it before. We have a magnet. There are some times where we try to bring two magnets together and they keep repelling each other. That is because of both of them are like poles. So, and there are sometimes we bring it, they attract, they are like poles. So, physics has explained that. So, from the experiment, a relationship can be made, and the relationship is called the law of magnetism, which states that like or similar poles repel, while unlike poles attract. So, this is the illustration of what we are talking about. So, we have north pole, we have south pole, they attract. We have north pole and north pole, they repel because they are like this one like poles. And we have south south, they repel. This is what I demonstrated. So direction of magnetic field. Since we said magnetic field is a vector field, so we expect a task direction. So we have experiments to prove the direction of magnetic field. So we have an iron filing experiment, and it's the direction is called the field pattern. So these are just illustrations for direction of magnetic field. So for the field patterns with iron filings, this is just what we can do. Place a thin sheet of glass over a bar magnet and sprinkle some iron filings. Tap the glass gently and notice how the iron filings arrange themselves in a clear, definite pattern. The pattern of the iron filings show the form of magnetic field. The filings are seen to arrange themselves in a series of closed loops around the magnet extending from pole to pole. So this is what we are trying to see. If you place iron filings in this one like this magnet, and we tap it gently, we'll notice that it will be like the filings are going from one end to another end, forming something like this. So they cluster to something like this. This is what we're trying to explain. Then we have magnetic field pattern or magnetic line of force. So that imaginary line, like the line we see the iron filings going passing, we refer that as magnetic line of force. But in real definition, it is defined as the line along which a free north pole will tend to move if placed in that point, or a line such that the tangent to it at any point give the direction of the field. So note, line of force in magnetic field never cross. So if you notice it, the um the line of force always go from north to south. So this is just an illustration of what I said now. So this is the north pole, this is the south pole. We have the arrow is going from north and is coming to south. So this is just a force of attraction in a bar magnet. This is for like poles. This is for unlike poles. Unlike poles, this is the north pole, this is the south pole. They attract each other, making the line of force moving from the north to the south, which are attracting. But these are from unlike poles. We have the north, we have the north. This one is going to look for the south pole. This one is going to look for the south pole. Since both are north, they will not attract.